We spoke a lot today about open software solutions and standards. It is high time we talked about hardware. Our next speaker is Yuri Myakochin, Executive Director of the Milandr company. He will inform us about migrating company solution from the ARM processor architecture to the open and increasingly popular
Good afternoon,
Risc-V
colleagues.
architecture.
I'm glad to see you all. I would like to talk about the progress our company is doing while developing microcontrollers and microprocessors based on the new Risc-V architecture. But first, I'll tell you how we moved in this direction. Milandr was the first company in Russia to license microcontroller cores from ARM in 2013. We believed that microcontrollers based on this architecture were widely used in Russia, and therefore, if we released microcontrollers with a similar set of peripherals and the same core, then we would be able to occupy our market niche. This decision was correct, and over time we actually figure out that in Russia the foreign ARM microcontrollers that were popular in Russia at the time are being replaced with our microcontrollers. This went on for quite a long time, several years, but about 2 years ago our company made a new decision. That is the analysis of the dynamics of architecture development in the microprocessor market and the need to acquire licenses from ARM for each core led to a decision to smoothly transfer our products from the ARM core to the Risc-V core. The fact is that by now the Risc-V kernel is quite widespread. Design tools and debugging tools are beginning to appear, and most importantly, engineers are becoming familiar with this architecture. Moreover, Risc-V attracts both young and experienced developers as a new trend, a new direction. So, now our company is developing 2 lines based on this core. The first line is a microcontroller, which we plan to use mainly for the electric energy meter market. This market is growing widely and rapidly, and the market in Russia is large. And most importantly, the Russian government supports the use of domestic hardware components, domestic microcontrollers in this direction. Thus, the release of a domestic Russian microcontroller will allow us to find a fairly large gap in the market for these devices. Before that, we already released microcontrollers on the ARM core with a similar periphery, and now we have redesigned our microcontroller by replacing the ARM Cortex-M3 core with Risc-V, technically keeping the same periphery as in the previous controllers. The only thing is that we have increased the memory size and added several functions that the current Russian legislation requires for this kind of microcontrollers. The second direction is microprocessors. They can be used in industrial controllers to build automatic control systems. In comparison to microcontrollers, the requirements for these microprocessors are broader. It is required to be able to run operating systems such as Linux or QNX, or these microprocessors can control all kinds of systems built into the automatic control system. So now I would like to dwell on my detail about our first microcontroller. It is a microcontroller for electric meters. On this slide you can see the main characteristics of this microcontroller. In general, the composition of the microcontroller itself is quite standard. It allows you to build electric meters with a minimum set of element base. The most important thing is that it integrates 7 sigma delta 80 ADC channels, which allows obtaining current and voltage value for electric meters. The hardware accelerator for calculating primary values from the recorded value of current and voltage, as well as the Risc-V core, which controls this entire system. In addition, inside the microcontroller, there is a fairly wide periphery. Most importantly, the accelerators are added to it for the implementation of both foreign and Russian cryptography. Also, there is a random number generation for these functions. It will produce in a fairly small sized QFN88 package. So, as I said, there are three main blocks inside this micro circuit. The first block is a 7-channel ADC block for receiving external current and voltage signals. Sigma delta provides a large dynamic range, sampling frequency of up to 16 kHz, and receive data after processing and transformed to the microcontroller. The microcontroller is built on the Risc-V architecture. As I said, there is an accelerator unit for processing cryptography. It accelerates all current cryptographic standards, the conversion of our products from Cortex M3 to Risc-V will, in principle, be fairly straightforward. As you probably know, to design software for Cortex M, two development environments are mainly used, namely Kale from ARM and IAR. At the moment, our microcontroller with the Risc-V architecture is also supported by the IAR development environment. So if the developers have precisely used the IAR development environment, then the transition will be quite simple for them. I would like to note that the capabilities of RAM and flash memory make it possible to build rather complex devices. On this slide, you can see a photo of the integrated circuit of our microcontroller. You can see its dimensions as well as the topological blocks inside the chip. The microcontroller is made using TSMC 90nm technology, which provides quite attractive price characteristics of the final micro circuit. As I already said, cryptography support is implemented inside the microcontroller. To fully implement this support, we have implemented additional characteristics into the topology itself. First, as you can see, the chip is completely covered by the power supply buses. If someone wants to invasively connect to the microcontroller, the system will be informed about an abnormal penetration. There is also an OTP memory where you can store encryption keys, and this makes it possible to fully implement the requirements put forward by the relevant Russian organizations. Now, a few words about our second microcircuit. As a rule, customers expect from a microcontroller that the microcircuit is released in a small-sized package and provides all the functionality that is required from the system to the fullest degree. Therefore, this microcontroller integrates ADCs, DMA controllers, and memory in order to reduce external modules. Customers expect high performance from more powerful processors, preferably multi-core and high-speed interfaces with external devices. It doesn't need to integrate as much of the primary periphery as possible, but does require the chip to be reliable, low power, and high-performing. This slide shows the structure of our microcircuit, which is under development. There are two 64-bit Risc-V cores inside that provide high performance. Our benchmarks show that this dual core performs better than ARM's Cortex-A9 core. Of course, both out-of-order execution of instructions and coherent multi-core configuration are implemented here. The structure of the microprocessor itself is classical. There are caches of the first and second level. The first level cache is connected directly to the cores. The second level cache is shared between the two cores. There is also a debug information support module. We are currently using the GCC toolchain to design software for this processor. Firstly, this toolchain is developed by the community and allows you to quickly adapt it to new processors. And most importantly, GCC can be used to compile Linux kernels in order to run on our microprocessor. At the moment, we have debug systems built on FPGAs where we run Linux kernels and custom software, and thus debug the interaction inside the microprocessor. Now about the launch. At the moment, we have not made a final decision on the technology that this microprocessor will be released on. We are in the process of searching, analyzing, and choosing the best solution. In this table, you see our current vision. We chose between 28 nm and 40 nm TSMC processors. Both options have their pros and cons. 28 nm technology means potentially smaller chip size and lower production costs, but higher investment in the launch of this microcircuit. With 40 nm technology, the opposite is true. The final microcircuit will be slightly more expensive than 28, but the initial investment will decrease. And most importantly, we know the 40 technology better because we already released several microcircuits using this technology, and as a result, the entire design cycle for such microcircuits is fine-tuned, which cannot be sent about 28. Therefore, we are now in a situation of choice, and the decision will depend on the market assessment for our microcircuits. If we see that the initial investment on 28 will pay off, then most likely we will choose this path, although it will certainly lengthen the development cycle a little from the beginning to the stage of sending the GDS files to the factory. So, I talked about these two directions. The first direction is the electric meters. The second direction is for industrial controllers. In principle, an industrial controller can be used in the same energy collection and metering systems. This allows us to offer solutions on two levels at once, at the microprocessor level and at the microcontroller level on the same core. In other words, at the level of sensors and devices, as well as the level of industrial controllers. This means that if some company develops devices in these two segments at once, there are many companies in Russia that produce both electric meters and industrial controllers at the same time, then the porting of the program code will be faster and the speed of starting development for these two systems will be less, because programmers can easily share program code, tell how to design these systems for both cores. That is, there is a unification within these systems. Before that, we had unification at the ARM core level. For example, ARM Cortex-M3 was used in a meter, and then ARM Cortex-A9 was used in an in an industrial controller. Now we are moving to the Risc-V core, both in metering devices and in industrial controllers. We hope that this approach will allow us to quickly enter the market and take a large share of the industrial energy market. And I hope that the support of the Russian government will help us to do this.
And I again have the opportunity to greet our speaker in our studio. And I am inviting Yuri Myakochin to answer your questions. Good evening, Yuri. Good evening. Well, the conference is coming to its end, and I'd like to ask you to share your impressions about today. I'd like to say that the conference is very interesting. It touches quite a broad cycle of tasks and problems, and I think that for many listeners, for many participants, there are many things to think of, and to work on this direction. So it is a very interesting direction, and I hope that it will be continued next year. Thanks. We hope also. Thanks for that word. So Risc-V, there is so much hype around it. What would you say? Is it possible within the next 5 years that the devices working on that architecture will take a big market share and somehow move the ARM? Well, I would say yes, indeed, because Risc-V is now in the same condition as ARM was when it started, but Risc architecture allowed for moving forward and take its share. Speaking about Risc-V, it is quite similar because we want to somehow set the flame. We have the wood, we have the fire, and we want to make a fire. But if you are adding some additional ingredients, the fire will be set instantly, and it will be get hit by itself. And I think that Risc-V at this very moment is in the same condition. Risc-V is supported by the community. There are some microcontrollers, microprocessors, including those that are developed by Milandr, and this flow cannot be stopped. It's speeding up, and it's moving to set its direction to set itself as a big market player. ARM won't go away, because if we're speaking about microprocessors and microcontrollers, it's not only the hardware, it is also software for that created specifically for that architecture. ARM has been here for 30 years, maybe more, and there is a lot of software for that. This is why it is still with us, and it helps ARM to exist. And Risc-V is a new direction, but there are many players who are involved, and there is some interest related to money to develop something, for something to develop, to grow. This direction should be economically beneficial, and the communities are now somehow distancing from architecture provider ARM, and there is a risk that the development that ARM was developed by ARM before should be done by the community. And I think that Risc-V is expecting a bright future. Well, thanks for this answer. It's a very interesting answer. I think that in the next 5 years we'll see. Could you estimate the economic benefit of migration from ARM to Risc-V? Does license purchase saving worth whole microprocessor controller microprocessor redesign? Yes, it is. It strongly depends on how much you sell, because you don't need to invest to buy the new cores from ARM. The thing is, Risc-V has open implementations, and in this regard, to redesign or to relaunch the microcontrollers, the prototypes, it is really easy. So the investments are not that high. Well, you have already answered this question, but again, what are the main advantages of Risc-V? Well, the main advantage is that it's new. When we are talking about software, it is both pros and cons. The pros is that the architecture is well known and it is being used and developed, and the cons is that it is really hard to change it. For instance, trying to replace it with some Intel x86, it was a failure. Well, this is the same with ARM, and ARM is quite an old architecture. There is a lot of code, but life is going on, and you need to reproject the command system. And Risc-V is taking its place. Having the experience we have, we can create the system of commands more effective than ARM, and I believe that this is our advantage. And developing your answer, what is the benefit of moving to Risc-V? Well, it depends how well it is. If we are moving from one architecture to another, if regarding the program codes, it's really hard. But taking the high level C, C++ languages, so switching between one architecture to another is quite easy. So Milandr is working, what we were doing was based on ARM, and we moved from ARM from one architecture to another. It wasn't a very difficult task for us. So the question from Vyacheslav: how would you estimate the maturity of the current code base ported to Risc-V? You mentioned GCC, Linux, and user code. How much of additional work was needed to launch your software for your purposes? Well, it wasn't not a big team. The main thing is that the code is open, and you can use the developments from other companies, and it is not a big company, and with such a small group we did that. Based on your experience, what is the best practical implementation of Risc-V? We consider it for microcontrollers and for microprocessors. On the server level, it is going to that direction, but it is still under development. If we are talking about signal processing, I know that Allianz Risc-V adds new systems of commands very open to support those accelerators. So I think Risc-V has its chances. And a question from Alexei Merzlekov: what would be the power sources of new processors? Will it be your own production, or will it be China, Taiwan? Well, we have our own microchips. We are sending them to the factory, and we choose the factory. Well, it is not really important. Usually we use the factory USMC, we are well aware of their technologies, of their code, of their experience, because when you are developing a chip, sometimes the chip design itself, the development of the road of the, well, it is very time consuming compared to the other. So we well know USMC, and we usually use them for this factory for building our microcontrollers. There is, so if there is some factory that would be the collaboration that would be more beneficial, we would choose it. Thanks a lot. Thanks. See you in the future.